One important point that we always are willing to cover is the fact that in everything that you're gonna see, starting today about spectroscopy, about evaluating the dielectric function, the polarizability, either in TDDFT or with the pedesalpeter, is about calculating a microscopic quantity. Always a quantity that depends on many indices. In principle, with the pedesalpeter that contains really a lot of arguments, we will have a lot of indices. And at the end, we want to make a connection with the real spectroscopy. So we want to make a connection with measurable quantity that are not necessarily microscopic, right? So we have to make this connection. So in this lecture, I just wanted to point it out how to make this this connection, and in particular for these quantities related to measurement done on solids, because it's very often where the more ambiguous definition can be. It's different for finite system. It's much easier, even if it's not obvious to do the comparison, but it's much easier to define quantities. Okay? So as usual, feel free to interrupt at any moment. Also because there will be a test at the end. Okay, so we haven't seen this yet, but you probably know it already, or you have seen it when you studied Maxwell equation, even classical electrodynamics. You know that there is a connection, in this case, linear connection between the electric field and the electric displacement. And so typically in linear response, if you assume linear response, you write it in this way, where you have a field that is related to the external charges. It's an external field, but you want to know what is the field inside your medium, and this depends on your inverse dialectrical function. And you can write the same thing, and this is what Valerio will use for TDDFT in particular, but we will use it also for the pedesalpeter, is in terms of potentials. You see, it's very similar. And what this says is that if you apply something, a potential in one point in space, a certain point in time, for example, here would be an R prime, you want to measure what is the effect of applying a potential in R prime, you want to measure in another point in space, in R. Of course, if the system were homogeneous, you will only have the dependence on the distance, because it would be the only thing in an homogeneous system. So here you will have R minus R prime. Since the system normally is not homogeneous, so it's not depending only on R minus R prime, it depends on both the points in space. But since time is homogeneous, it doesn't depend on when you start applying the perturbation. You apply perturbation, and after a while, you see what happens. So it depends only on the difference of time. If you start your experiment today or tomorrow, it should be the same, right? And in fact, it depends only on t minus t prime, which equivalent in Fourier space becomes only one frequency. Okay? And so this is a definition in terms really of quantities that are microscopically described. Depends on each point in your space, in R and R prime. So it's a quantity that clearly is not necessarily the one that you see in an experiment, right? This quantity here. So what do we see? In experiments, it's something different. You typically see one number or more than one number, because you can have different experiments. But you typically see, for example, in the case, this is an example of the loss function that you measure in electron energy loss or in elastic X-ray scattering. You see one number in terms of the frequency. You can also have the momentum transfer, so it depends on how you put your detector. You will have different loss function, so it can depend on Q and omega, but it definitely doesn't depend on R prime, because you don't apply these things microscopically in different points in space, and you don't measure in different points in space as well. Okay. This is the thing that you have in the experiment. The same for example, the optical absorption here. I try to use the same pictures. So in an experiment, here is a setup for inelastic scattering. This is an ellipsometry setup. Okay, this is what we have. And so we want to do this connection. Now you can already imagine what could be the connection, right? So we have something that depends on, for example, the loss function was imaginary part of the inverse directed function. The absorption, like this case here, it's the imaginary part of the macroscopic directed function. So I ask you, what do you think could be the connection between this quantity that depends on R and R prime to this quantity that is just a number, doesn't depend on R and R prime? What could be the connection? What do you think? Because what we calculate is something you will see in RR prime or GG prime if we want to work in reciprocal space. But we want one number. So what is this number? If we have this epsilon microscopic. Any suggestion what it could be?
Yeah. If I understand the question correctly, actually, it gives the resonance at this particular energy.
Yeah, but the point is that this quantity, indeed, it has a resonance. So at a certain moment, we'll have, for example, a peak, but it depends on R and R prime. But we don't measure this in R and R prime, right? What we measure is a number of your system.
Okay, that's a propagation going to an excited state and coming back. I mean, it moves from excited.
Yes. And what we evaluate numerically is this quantity here. Yeah, but what we want at the end is one number for frequency. For each frequency, we want one number, right? Yeah. While here, we will have n square number. Each number for each R and R prime, depending on our grid in real space or our grid in G space, we will have n square numbers. Too many. So, what could we do?
It's an average.
It's an average. If you take the average, in fact, it is an average. We'll just have to verify what kind of average to do in order to be meaningful. And an average is not something ambiguous per se. For example, if you had an atom in your, you define what is your system, your box, you could say you have a quantity. You might want to discretize the space. If you want to do this, you have a function in each point of space, and you do an average. You calculate the integral of the function in all the points, and you divide by the volume. And this is the definition of essentially an arithmetic average. So, and this indeed gives one number. So it's a macroscopic one. And this is what we want to do. We just have to pay attention now when we have the solids, what kind of average we have to do. But in terms of the procedure is actually that simple. And now again, for a finite system, since you have typically quantity test the case, your system, you can always decide if it is inside your measurement lab, you can define something. And instead, when we have a solid, especially when we treat solids like we do with periodic boundary condition, so your system is essentially infinite. So deciding what is that you take as your average is to be specified well, to be carefully specified. Okay? Because otherwise you don't know where to take the boundaries because your system is infinite. Okay, so mostly this concept were known since the work of Adler and Weiser. I found that have been a little bit more explicitly explained in this article of the Sottile and Fiorino. And to use two-day notation with a lot of details. There is this book, which is a collection of several long review articles. It's very well done. Okay, so this you can check. Okay, so for a system that is described in reciprocal space, we have to do this average, and so, well, we can apply the average operation on a function that depends on R. This is for a function with only one space variable. So we expanded in reciprocal space, and we separate, and there is a reason for that. We separate the part that depends on G and the parts that depends on Q, because very often when we do average of quantity, when we do measurement, we don't integrate necessarily over all possible momenta. Typically is the case of electron energy loss, in which you arrive with an electron. This is the same for inelastic history scattering. You arrive with an electron, this is scattered at a certain angle. So now if we put the detector at a specific angle, that means that we are selecting a momentum transfer. There is a K initial and a K end, so there is only one Q as an exchange momentum. So if we do not integrate over all Q, we don't want also to do this integration over Q. We will need something that depends on Q. So we want to keep this, okay? Because many of the experiments are resolved in Q, in momentum. So we have this quantity here, that is a quantity that is oscillating, but is also periodic. This what saves us, because this quantity is periodic. In fact, if you here substitute in the place of little r plus any vector of your cell size, you will obtain again the same result. And so that means that we now can integrate that in a non-ambiguous way, because it's periodic, so we can do the average in any of the cell, it will be the same result. And so if we do the integral now of this will be the integral only of the only part that it exists in R, and you might remember that this is a delta function of R0, G0, sorry. So that means that this will give you a delta capital G0. So that means that the only place that will resist of this is the component G equals 0 of this sum. So at the end, taking the macroscopic average of a function in R corresponds to go to the reciprocal space and take the G equals 0 component, the first component of your Fourier quantity. Is it okay that? Because from the physical point of view, this is crucial and also mostly the most important point of this. Okay? So if you can transform it in reciprocal space, typically for all these quantities with periodic boundary condition, it means that you take the first component in reciprocal space. And that's the average. Okay, so this is the important point. And now you can do it for a two dependency space, like for the inverse directive function. You can do the same. You can go to reciprocal space, get the part that doesn't depend on Q specifically, because we want to maintain that. We have a part that depends on GG prime, Q and omega and R prime. We integrate over R and R prime. And when we integrate that, we define this as a macroscopic quantity. It's the inverse dielectric function. And again, what will be if you do this, this integral? Well, we will have a delta function coming out from this integral over R, and another that comes from this integral over R, right? And so, not strangely, not astonishingly, it will be again the 0, 0 component of your quantity written in Fourier space. So, for example, typically this becomes like a matrix in GG prime. And so you take the head of the matrix, really the first element. And this is your macroscopic quantity. Okay. And so, well, this will be explained later on by Valerio, the relation between the inverse dielectric function and the polarizability. But at the end, that means that, for example, for the yields, you take minus imaginary part in the inverse dielectric function, you get that component. So you have to solve in one way for chi, typically in DFT, or with a Bessel filter, or with other methods. Once you solve it, you obtain epsilon minus 1. And from this, you take the 0, 0 component, you put it here, and you will have your loss function, and you compare with the experiment. And like we said yesterday, this quantity, epsilon or epsilon minus 1, are in absolute units. So the number that you get out of it should be exactly the number that you compare with the experiment. It's not to be rescaled. It's an exact value. It's not in arbitrary units, okay? And in fact, this afternoon, what you obtain is this quantity here, and you can compare with the experiment, and what you obtain is the real the quantity, the absolute number that should this function should have. And you can compare, for example, this is what comparison with electron energy loss experiment at vanishing momentum transfer. So this Q is very, very small. Like Simo said yesterday, typically with electron scattering, it's better to go small momentum. And instead, when you do elastic Israel scattering, you have better resolution at high momentum. And so this is one particular comparison between theory and experiment, and you will see this today. And now comes absorption. And absorption, you see, is defined either by in an ellipsometry, like the imaginary part of epsilon 2, or by doing the Lambert law, you have alpha, which is also related to the epsilon 2 and kappa. So they are all related, this quantity. And so we want to calculate this. And this is the imaginary part of epsilon, the macroscopic dielectric function. It's not the inverse dielectric function, right? So here we have to pay a little bit more attention to what we define. So this is the definition as a linear response function. So the quantity epsilon minus 1 as a microscopic quantity is a linear response because we have on the right here the applied field. We apply, for example, a field in R prime, and we want to measure in R. So we have here the quantity that we can change at will, right? I don't know if you remember from the linear response theory. You have on the right the quantity that you can change at will. You have a knob where to change, and on the left you have the result of this. And in between there is the relation, in which case the linear relation. Okay, in order to be considered as a generalized susceptibility, you have this important point to be valid. Okay. So now you would say, well, I have the epsilon minus 1, G prime, and Q, and omega. I can invert it. If I have the whole matrix, I can invert it. So I have my dielectric function in Gg. And so I could take, as we know now, in order to take the macroscopic average, I could take the 0, 0 component. And I could define the macroscopic dielectric function has the zero component of my epsilon, right? And unfortunately, this is wrong. You cannot do that. And that means that we have to verify what is specifically here now that we are considering with absorption. And the point is that with absorption, we have something different. So in our equation that is the correct equation where we have epsilon minus 1, you see, in order to obtain this quantity macroscopic is quite easy because we said, okay, let's suppose that we apply a macroscopic field here. That means G prime means 0. So this is a macroscopic quantity. And if you want to measure a macroscopic response, it's easy. We take the 0 component. And so here we will have the 0, 0 component. So it's easy to verify what is the limit of the macroscopic, let's say the macroscopic limit of an equation when it's written correctly. It's written in the correct way. And now we ask, for example, if we apply a macroscopic field, typically the case of a plane wave incoming, which is extending the whole universe, no? And we want to verify what is the response, again, macroscopic, we know how to do it. And the point is that in the macroscopic world, and this again, you probably now remember, that you always seen the equation written like this, didn't you? Typically, D is equal epsilon E, which is not wrong. It's also correct, but it's sort of the other way around. Which is which? If you look in the Jackson book, you will have it mostly like this. And why is that? Why we said that this is the correct way, and sometimes you have seen it like that. And in fact, they are both correct, but they do not work in the same realm. You see that here I didn't specify R prime. These are macroscopic quantities. And in the macroscopic world, we have to verify what is the quantity that goes on the right, the quantity that we can change at will. And unfortunately, for example, for a photon, we can consider, for example, as a plane wave incoming, this perturbation is much bigger than the system that we want to consider. For example, even the wavelength of a photon in the visible range, for instance, it will be bigger than the cell. Unit cell will be sub-angstrom, and your visible light will be what? 600-800 nanometers, much bigger. Right? So it's seen as a field that is much larger than your system. The variation are on a range that is much larger than your system. And so in that case, we have to verify what is actually the quantity that we change at will in order to write this equation correctly. This way or in this way? What is the one that we change at will, D or E? And so we can verify this with a simple example in which we have a system and we have our, for example, in this case, electric field, but we can do the same for a magnetic field. So we have the two things that, the two fields that define your electromagnetic radiation. You have the electric field and the magnetic field. Here I put only the example of an electric field with a condensator, but I could also put a big solenoid around the whole system would be magnetic field. Okay? So the point is, let's suppose that we have a situation in which my electric field, for example, contains the system. So it's much bigger than the system, which is exactly our case here. For the case of absorption, when we are coming with a photon. So if the system is contained and we apply, for example, an electric field, we can have here our variator, so we start changing. And once we change, we want to know what is the field, the tension that we are applying to the system. And so you apply a voltmeter between, for example, here, which is equivalent here, and we look at the voltage that we are applying, right? And the point here is, what is this voltage measuring? So we have a certain tension that is applied from our variator, our battery, if you want. But there is also the fact that the system here polarized, right? If you apply a tension, immediately there will be charge going on one side and depletion of charges from another side. So what you measure in the voltmeter here will always be a total effect of what is your tension and the polarization of the media, always. You cannot distinguish between the two. So what you are changing at will, essentially, is the sum of two potential, but you don't know in which way, but this is the quantity that you change, is a total potential due to the fact that you are applying a field, and your system also polarized that changes the voltage between the 2 points. So what you apply in the moment in which you have a perturbation that contains the system, you always have something that is a total field, not just the external field alone, as it was completely separated from the system itself. So you apply a total field. So that means that this way to write the things, when you are in this situation of a system that P is smaller with respect to our perturbation, you will have an equation that is written like this, because it's the total potential, the one that you vary at will. And so now you can make the connection. From the microscopic world, you will write it like this, which is correct. In the macroscopic world, you write it like this, which is also correct. So this D, it will be this D0. This E, which is macroscopic, it will be your E0, only the macroscopic component. And so you can figure it out now. If this is this and this is this, your definition of macroscopic dielectric function will be the inverse of that thing. So your macroscopic dielectric function is not the epsilon macroscopic, epsilon 0, 0. No, you have to do the inverse dielectric function. From that, you take the 0, 0 component, you obtain a number, you invert this number, and this is the macroscopic dielectric function, which seems more involved, but it's the real quantity to be compared with the experiment. And this is different from epsilon 0, 0. Would you know what is the difference? So if I say, this is the macroscopic dielectric function, which is epsilon n, and we say that it's different, completely different from epsilon macroscopic, which is 1 over epsilon minus 1 macroscopic component. And this is different of taking the dielectric function, dielectric matrix, and taking the 0, 0 component. These are different. In what they are different? What do you think? Besides the fact that mathematics is not the same.
But there are also no diagonal components also.
Exactly. Exactly. So you see, let's reformulate the question as suggested. If they were exact, when taking an element of a matrix is equal to taking the inverse of the matrix inverse taking one element. Only in one case, when the matrix is diagonal. If the matrix is diagonal, you invert it, you obtain new elements, and these elements are the inverse of the original matrix elements, because the matrix cannot mix if it does not diagonal component. So what is this? So That means essentially that in here we are taking into account the non-diagonaliticity, let's say, of the dielectric matrix. But for example, when this matrix will be diagonal, so diagonal in G, so that means delta GG prime. What does it mean in real space? If it is diagonal in G, in real space, it depends how on R and R prime.
Can I ask a question?
Yeah.
Maybe naive one, but usually when we deal with matrices and we calculate some averages, we take a trace. The trace averages is basis in the problem equation.
Yes.
It is chosen on purpose so that we don't care about all the abnormalities. Why in this case, when we are talking about macroscopic average, we do not use trace operation?
Oh.
Because then we do not care about all the abnormalities. This would be mentioned. Is there a reason for this?
Well, the trace of the matrix has a usefulness and has its meaning. It's just not what we are after. So a trace of the epsilon, indeed, if you write this in another basis, for example, people use not necessarily plane waves, you can use a Gaussian, you can use other bases, you can write it directly in real space, and indeed, traces of the matrix are the invariant, and you can use it, for example, to test your implementation to verify that you're okay. The point is now that since the beginning, we were not interested in a specific, for example, quantity of your matrix. We were interested only, so since the beginning, the question was, what is the average of this matrix? What is the macroscopic average? So the macroscopic average has a definition. So I want the integral in R and an integral in R prime of a function. So this is not related, or probably will be in some way related to the trace, but it's not specifically asking what is the trace. So I don't know if we actually can use this fact about the trace of the matrix to simplify the problem. I don't know, but for certain, I'm not using this as inside my original question. So my original question was really, I do this average, and now I was tempted by the fact that epsilon itself is a matrix, because if epsilon to the minus 1 is a matrix, I can invert it, I will have something that I can call epsilon GG prime. And my point was, if epsilon GG prime is also a dielectric matrix, I can take the 0, 0 component, and this will be a macroscopic. And yes, this is a macroscopic quantity, but it's not what I would define the macroscopic dielectric function, because the real one is this. Now, what I'm asking is, but if the matrix at the beginning were diagonal in GG prime, this would be the same. Yes, it would be the same. But I'm making an assumption here, no? Why the matrix could be, how could it be that the matrix in GG prime is diagonal?
Non-interactive?
Well, what do you mean by non-interactive? So you have, for example, in GG prime, you have it diagonal. So what it would mean in real space? So if it is diagonal in G space, in real space, what would be the dependence with respect to R and R prime?
It's only the difference.
Exactly. It's only the difference. So when it is depending only on the difference, that means that your system is homogeneous, an isotrope. Because you apply a potential here and you measure it here, it would be the same that if you do the same calculation like this. It will only depend on the distance. So that means that the system is homogeneous, if you can do that. So when the system is not homogeneous, then we say that it contains crystal local fields. Then these crystal local fields are contained in the non-diagonal component of your epsilon, and so they have to be taken into account. So that means that you cannot calculate epsilon, you have to calculate epsilon to the minus 1. And then only after you calculate that, you can take the 0, 0 component, and then you invert it again, which is just a number to the inverse of a complex number. And that's the correct way to do it. And this is in fact what is coded in the code and what you're gonna verify. And what you can also verify is how much is this crystal local field. So you can imagine that your matrix is diagonal, so you neglect components. In the code, it's always cheap to do this calculation because you just put to 0 the other component, and you verify what is the difference. You see how much this taking into account the non-diagonal component is important. So you will do the test. It's one of the exercises of this afternoon. And so I can conclude, once you have the macroscopic dielectric function, you can calculate the absorption. We have solved what you use for the yields and inelastic scattering and many other related quantities. You've seen some of these quantities also in some of the posters. You will see that there are different quantities to be evaluated. Okay? What time is it? Okay. So now, let's do a little test. If you can take your telephone out, you can go to the website, it's called wooclap.com, so www.clap.com, and put the flag CCAM24. Okay, let's go. First question. Inelastic scattering and electron energy loss are related to the same function, even though the prefactor might change. Which one? I have a few seconds. The real part of the dielectric function, the imaginary part of the dielectric function, the spectral function, or the imaginary part of the inverse dielectric function.
One difference.
Good. You want to give some bad answer to verify someone. Okay, so as you can imagine, the correct answer was that one. Okay, good. Let's go on. Which quantity gives the absorption step? So the macroscopic dielectric function, the imaginary part of the macroscopic dielectric function, or the real part of a combination of real and imaginary part of epsilon. Again, few questions, few seconds, sorry. Get on with it. Valeria. So far, nobody bite bait. Okay, great. This is correct. Of course, as far as I see only one here, there is no problem. Now, this you should also have listened to previous lecture. But so, what spectroscopy would you use to measure the optical gap? Photoemission spectroscopy, ellipsometry, photoemission plus inverse photoemission, and inelastic scattering. Okay, now here we see a bit more variation. Okay, here there was not a trap, but anyway, there was a little thing because I asked how to measure the optical gap, which is not the photoemission band gap. So the correct result is not photoemission plus inverse photoemission. That would indeed give you the fundamental gap, the photoemission band gap, but it will not be the optical band gap. Because in photoemission, you remove one electron from the valence state, then you put an electron with inverse photoemission into the conduction state, and you measure the energy difference of these events. And this will give you a gap, of course. In an optical gap, you do not move, you do not expel electrons, you do not gain electrons. in an optical situation, you absorb a photon, and the system goes from a ground state to an exact state, still with n electrons. And so this is could be similar, but it's another gap. Okay? That you measure in ellipsometry. So both today and on Friday, we will treat about these neutral excitations, like the optical gap. And for the photon emission gap, you will have to wait on Thursday, when we indeed talk about the Green's function approach to obtain exactly these kind of things, removing an electron, putting back an electron, and so we describe these things. And finally, what is the main feature? It's not by far the only one, but it's the main feature that you get from the loss function that you measure in electron energy loss or in elastic X-ray scattering. So you can measure, but is it the main feature? Absorption peak, band gap, Higgs boson frequency, or plasma? Okay, there is an overwhelming majority for plasma, which is indeed right, which doesn't mean that you cannot extrapolate sometimes band gap, very difficult, and definitely you will see some absorption peak, but it will not be the main feature because of how the loss function is constructed. It's epsilon2 divided by epsilon1 squared plus epsilon2 squared, and so the epsilon2, even if it is big, it will be bigger in the denominator, and so you will get wash out. So you will get a signal only when you have this epsilon equals 0, both, or let's say small, both real and imaginary part, and so that means the plasma. This was the correct one. Great, thank you for playing the game, and of course there will be other tests coming out, but now we move along because we want to know how we actually calculate this epsilon. Okay? And so I will leave the floor to Valeria.